Good evening. We are going into the second session of our third chapter, Motion in a Plane. So in the first part we discussed about how you can add two given vectors A and B using the triangular law of vector addition and also the parallelogram law of vector addition. If you have more than two vectors, then of course you can use the polygon law of vector addition. So what we discussed last class was that if you are given, let's say, two vectors A, vector A and vector B, then by the parallelogram law of vector addition, the two vectors that are to be added should form the adjacent sides of a parallelogram starting from a common point. Then you complete the parallelogram. The diagonal of the parallelogram starting from that common point will give the resultant of A plus B both in magnitude as well as direction. So that vector R is equal to vector A plus vector B. Now you can find the magnitude of this vector R by the formula root of A square plus B square plus 2AB cos theta, where A is the magnitude of vector A, B is the magnitude of vector B, and theta is the angle between the two vectors that you are adding, A and B. Then if R makes an angle alpha with vector A, you can find the direction of R by tan alpha equal to B sin theta by A plus B cos theta, where you must know that this alpha is the angle that the vector R makes with vector A, and you can find out the direction that vector R makes with vector A using this formula. So this is what we discussed in the last class. Now here we have some special cases where suppose we have the two vectors A and B which are perpendicular to each other. Let's say you have vector A and B along the x and y axis. So this is vector A along the x axis. This is vector B along the y axis. Vector A along the x axis, so that they make an angle of 90 degree. So now if you complete the parallelogram, the resultant will be given by this vector R, and theta between the two vectors is cos 90. Cos 90, as you know, is 0, and therefore you have the resultant simply given by A square plus B square, root of A square plus B square magnitude, and sin 90 is 1, so this will become B, and cos 90 is 0, so this whole term will be gone, and you will have tan alpha as B by A, alpha being the angle that the resultant vector makes with the vector A. So that you see from this right angle triangle, this is vector B, so here this is vector B and this adjacent side is vector A, so that tan alpha will be opposite side by adjacent side. So this is a special case when vector A and B are perpendicular to each other. You can have another case where the two vectors A and B are in the same direction. In that case, we have vector A and vector B both parallel to each other in the same direction, so that theta is 0. In that case, the magnitude of the resultant will be root of A square plus B square plus 2AB cos 0. Cos 0, as you know, is 1, and so this is going to be A square plus B square plus 2AB, which can be written as, this is A plus B the whole square, so you may write this as A plus B the whole square. So the magnitude given as root of A plus B the whole square is simply A plus B. And direction in this case will be 0, the direction of resultant will be in the same direction as A and B, because tan alpha in our case will be B sin 0 by A plus B cos 0. Sin 0 is 0, so tan alpha 0 would mean alpha is 0. So you see, if there are two vectors that you are adding which are in the same direction, you simply add the magnitude of the two vectors and you get the resultant of the magnitude of the resultant, and the resultant will be in the same direction as the vectors A and B. And suppose you have vector A and B in opposite directions. Let's say vector B is in the opposite direction. So that the angle between the two is now 180 degree. Both are in opposite direction. So this becomes 180. Cos 180 is minus 1, and so this becomes minus 2AB. So that you have A minus B the whole square, and the magnitude of the resultant will be A minus B. The larger vector, the magnitude of the larger vector minus the magnitude of the smaller vector, and the resultant will be in the direction of the larger one. In the same direction of the, if A is larger, resultant will be in this direction. If B is larger, then resultant will be in the direction of B. So magnitude will be simply the difference between the two vectors. So this is how you would add two vectors. If the magnitude of the two vectors are given and the angle theta between the two vectors are given, you may use this formula to find out the resultant both in magnitude as well as direction. Now suppose your two vectors are given in the component form. In the last class, we discussed about resolution of vectors, how you can split a vector into the two rectangular components. So let's see, we have this as the y-axis, this as the x-axis. So we are talking about this xy plane. Now here, suppose we have vector A. This is vector A. You can split the vector A into its two rectangular components. The component along the x-axis, let me say, has a magnitude Ax, direction given by I cap. I hope all of you remember that I cap is a unit vector, meaning its magnitude is unity, but its direction is along the positive x-axis. Its component along the y-axis can be represented as Ay j cap, where Ay is the magnitude of the vector, the component along the y-axis. J cap is a unit vector along the y-axis. Unit vector has magnitude unity but direction along the y-axis. So the component, so vector A can be represented in terms of its components as component Ax I cap plus Ay j cap. These are the components of vector A, and vector A is represented in the component form. Now the other vector that we are going to add, let me represent it as vector B, which has, so this is Ay j cap and this is Ax I cap. Now vector B has its x and y components. This is Bx I cap and this is By j cap. Okay, so that vector B is now represented as Bx I cap plus By j cap, because you've split the vector into its two rectangular components. Now if I want to add the two vectors, applying the parallelogram law of vector addition, if I complete the parallelogram, the diagonal of the parallelogram, let's represent resultant here as a diagonal of that parallelogram. Okay, this is vector A. Okay, resultant given by the diagonal of that parallelogram. So that this vector R has its component along the x-axis as Rx I cap and the component along the y-axis as Ry j cap. So our resultant also has its component, which is Rx I cap along the x-axis and Ry j cap along the y-axis. So that I may represent R vector as Rx I cap plus Ry j cap, which I'll take as my first equation. Now if I'm going to find the resultant R, You know resultant R is what? Vector A plus vector B. This is vector A is AX I cap plus AY j cap. This is vector A plus BX I cap plus BY j cap, which is vector B. So to find the resultant, the AX and BX are in the same direction. So I told you, if two vectors are in the same direction, you simply add them. So since AX and BX both are along the x-axis, same direction, you simply add AX plus BX, and that will be along the I cap, plus then you have the y components, both those are along the y axis in the same direction. So you simply add their magnitudes as AY plus BY along j cap. This is my equation 2. So now if I compare this equation to this equation, both represent the resultant vector. So I may compare and write this Rx is actually equal to AX plus BX and Ry is equal to AY plus BY. So Rx is equal to AX plus BX and Ry is equal to AY plus BY. So we get a resultant vector in terms of its components Rx, which is a sum of the x components of both A and B, and the y component of the resultant will be the sum of y components of A and B. So that is our resultant vector. So once you know that, then you can find the magnitude of the resultant and the direction of the resultant. Going back to, let me show you that. So what we now have is, we have added the two vectors A and B, and then we have got the resultant as vector R, whose component along the x-axis we know is Rx I cap, and along the y-axis we know it is Ry j cap. So let this be angle alpha. So magnitude of our resultant is given by Rx plus Rx will be given by Ax plus Bx, and Ry is given by Ay plus By. So this will be the sum of Ax plus Bx, and this will be the sum of Ay plus By. So this is how you will add two vectors if the two vectors are given in the component form. And you can also find the magnitude of this, because you know Rx and Ry are two vectors which are Rx I cap and Ry j cap are two vectors which are perpendicular to each other. So we know the magnitude of R will be root of Rx square plus Ry square, and tan alpha here, tan alpha, this portion is Ry j cap. So this will be Ry by Rx. So you can find the resultant in magnitude using root of Rx square plus Ry square, and the direction that Rx makes with the x-axis, tan alpha, will be Ry by Rx. Rx and Ry you may get by adding the x components of A and B, you get Rx, and by adding the y components of A and B you get Ry. Okay. Now let us go into the next topic. So we've just completed addition of two vectors, and we are now going into our next topic, that is velocity, average velocity and instantaneous velocity. We have discussed both in the last chapter when we did motion in a straight line. We did instantaneous velocity and average velocity. Similarly, we did instantaneous acceleration and average acceleration. So it is not anything new to you. But we are now going into instantaneous velocity and average velocity. Similarly, instantaneous acceleration and average acceleration when a body is in two-dimensional motion. Okay. So we have our body as usual. I am always taking the body moving in the xy plane. I told you, you can take any plane, xy plane or xz plane or yz plane. But we've been continuously using xy plane. Okay. So let me say your particle is at P at time t1. Okay, so this is P, position P. So any line that joins from the origin to the position is what you call as the position vector. Here I'll denote that vector as R. So this R has its components along the x and y axis. I'll call this as xi cap and I'll call this as yj cap, which means if I split or resolve the vector R along the x-axis, the magnitude is x, direction is y. Along the y-axis, the magnitude is y and the direction is given by j cap. That means it is along the y-axis. So these are the two components of vector R. Now I may represent vector R as xi cap plus yj cap. Now after some time, let's say at a time t2, the particle moves to a new position P dash. So let me represent P dash here. So this is P dash. Now this is represented by the vector R dash. I hope that's clear to you. Vector R dash. Okay. So now it will have its own components. So if I resolve this vector R dash into its x and y components, this will be x dash I cap and this is going to be y dash j cap. The components of vector R dash are, so I will write R dash vector as x dash I cap plus y dash j cap. Now the resultant, that is the displacement vector, is a vector that joins the initial position to the final position. So from here, if I draw a vector in this direction, that is what I would call as delta R. So we have the displacement vector starting from the initial position and ending at the final position. So you will notice now that vector R is in this direction, delta R is here and vector R dash is here. So if you go back to triangular law of vector addition, we said if two vectors are added, they can be taken as the sides of a triangle taken in the same order. So you see R and R delta R are in the same order. The resultant will be given by the third side taken in the opposite order. So you see R dash is now taken in the opposite order. So this is head to tail. Head of R dash joined to the tail of delta R. So we add these two vectors to get the resultant R dash. So you may write R vector plus delta R vector must be R dash vector, or I may write delta R is equal to R dash minus R. Okay, delta R, my displacement vector is given as R dash minus R. So let's see what is delta R then. Delta R is equal to R dash in the component form is this. So that is x I cap plus y j cap minus R dash. So x dash and y dash. X dash I cap plus y dash j cap representing R dash minus we have x I cap plus y j cap. Now delta R is then going to be equal to, so you see this is happening, this is along both x dash and x are along the y axis, sorry, along the x axis. So since they are in the same direction, you can simply add their magnitudes. So here you have x plus minus x, that will give you x dash minus x along the I cap, and this is y dash minus y. So y dash minus y along j cap, which I may write as delta R equal to, this is this distance, so that is delta x. So I may write that as delta x along the x-axis, and the difference between y dash and y I may write as delta y along the j cap. So vector delta r, displacement vector, also has its own components along the x-axis, delta x along the x-axis and delta y along the y-axis. So this is how you will represent the displacement vector delta r. So now what we actually want is, we need to go back to find out the average velocity. Average velocity, as you know, is displacement by time. So average velocity represented as v bar, which is a vector, delta r by delta t. Delta r is this. So we need to divide both the components with delta t, which means we have delta x by delta t along the x-axis, plus we have delta y by delta t along the y-axis. This is displacement by time along the x-axis, which is velocity component along the x-axis. We may write it as Vx I cap plus, this is displacement along the y-axis. Delta y by delta t will be Vy j cap, which is our average velocity, having its own components Vx and Vy. So delta r components are delta x and delta y. Delta v components are Vx and Vy. Now please note that delta r and velocity, average velocity, will have the same direction, because you see this vector delta v, this vector v is dependent on the direction of delta r. So that means this is what you have as delta r. This is representing the motion of the particle. So the velocity of the particle will be in the same direction as motion. Please note that average velocity will be in the same direction as direction of motion of the particle, which is delta r. And the components of delta v and delta r also we have got. I'll make this clearer to you when we do a problem. Before we do that problem, let me also tell you what is instantaneous velocity. Instantaneous velocity is simply velocity at a particular instant. At one particular instant, let's say you say find the velocity of the particle at t equal to 2 seconds. So then we are talking about instantaneous velocity. So instantaneous velocity we already defined in the last chapter as limit of average velocity as the time interval tends to 0 or time interval approaches 0. So it was defined as simply v, no v bar. V bar is for average velocity. Instantaneous velocity is defined as limit as the time interval approaches 0, delta r by delta t, which is average velocity. So instantaneous velocity is defined as the limiting value of average velocity as the time limit approaches 0. So this is written as dr by dt. Whenever we have instantaneous velocities, the time interval approaches 0 and you represent it as dr by dt. So we have instantaneous velocity given as d by dt of r is x I cap plus y j cap. If you remember, vector r we had taken as the x component along the x-axis and the component y j cap along the y-axis. So this is also equal to dx by dt I cap plus dy by dt j cap. Dx by dt is velocity along the x-axis. So the component of velocity along the x-axis plus component of velocity along the y-axis. dy by dt, you can replace it with velocity along the instantaneous velocity along the y-axis. So we have our average velocity and the instantaneous velocity having components along the x-axis as vx, I cap and v by j cap. Now to get the direction, see, suppose your body is moving in the xy plane. Let's say this is the xy plane. Okay, your body, let's say, is moving in this direction. This is the motion of the particle. To get the instantaneous velocity at any particular instant, let's say at this instant, let's say at time t1, you need to draw the tangent to that curve, and that will give you the direction of velocity at that instant. let us check another instant here. Let's say this is at time, the body is at this position at time t2. To find the instantaneous velocity direction at that position, so at this position, this is what I said, the components are Vx and Vy. To find, position. So to find the direction of velocity at that instant, you need to draw the tangent at that position to the curve, and that will give you the direction of velocity. So instantaneous velocity direction is given by tangent drawn at that instant on that curve. So let me just make this a little more clear to you using an example. Okay. What we discussed till now about delta r and delta v and instantaneous velocity, we will just try doing an example. I hope that will be clear to you. Let us say the position of the particle r at time t1, when the particle was at point P, if you remember in our graph, at time t1, the components of r were given as 5i cap plus 2j cap. So along the x-axis the magnitude was 5, and along the y-axis the magnitude is 2. And then r dash, after some time it moved to a new position P dash, if you remember, and that happened at time t2. So that given by, let's say, 7i cap plus 6j cap. So it has moved to a new position P dash, whose component along the x-axis is 7 in magnitude and whose component along the y-axis is 6 in magnitude. So delta r, you know, is r dash minus r. So this is going to be equal to r dash is this. So this 7 and this 5, both are magnitudes along the x-axis in the same direction. So you may subtract. 7 minus 5 is 2i cap plus, this is 6 minus 2, that is plus 4, plus 6 minus 2 is plus 4 j cap, and so that is delta r, which means if you have this as the x-axis and this as the y-axis, we have delta r vector having its components as, this is 2 along this much, this is 2i cap, and the component along the y-axis is 4j cap. And this, let us say, is the direction. This angle will give you the direction that delta r makes with the x-axis. So if you want to find the magnitude of this delta r, that is the displacement vector, then you know your formula. The magnitude is root of what is the component along the x-axis? 2, and the component along the y-axis is 4. So you know this will be, I told you, when two vectors are perpendicular to each other, root of a square plus b square plus 2ab cos 90. So it's simply root of a square plus b square, or we took this component as x square and this we took as y. So we may write x square plus y square, which is root of x for us is 2, so that is 4, plus y for us here is 4, square that and we have 16, and that is equal to root of 20. So magnitude of delta r, let's say it's in meters, root 20 meters. What about its direction? How do you find its direction? Tan alpha is equal to, tan alpha, I told you, when the two vectors, the two components are rectangular components, tan alpha is simply opposite side by adjacent side. So to alpha, the opposite side is 4 here. So that is 4 divided by the adjacent side is 2, and we have tan alpha equal to 2. You can find out alpha from the logbook. So tan alpha is equal to 2. So we completely know the displacement vector. Its magnitude is root 20 meter, and we know it makes an angle alpha with the x-axis such that tan alpha is equal to 2. Now for this same thing, let us look at the velocity vector. let's see what happens to the velocity. Now suppose this change in position happened in a time interval, let's say t2 minus t1, that interval t2 minus t1, which is delta t, let's take it as 2 seconds. So this whole thing happened it moved from p to p dash in a time interval of 2 seconds. So then what happens is the average velocity is equal to delta r by delta t. That means delta r is 2I cap plus 4j cap by the delta t. Time interval we said is it happened in 2 seconds. So if I divide, I will get 2 by 2, that is 1I cap plus 4 by 2 is 2j cap, which gives you the average velocity in that time interval 2 seconds. So now we know the velocity components. So velocity, if I am going to represent, this is the x-axis, this is the y-axis, and so the velocity, average velocity vector, this is the x component with this Vx I cap. So Vx I cap is 1. Vx I cap is given to us as 1 I cap. This is 1 I cap. And what we had as Vy j cap. Vy j cap is here 2 j cap. And let's say this forms an angle alpha with the x-axis. So let us look at the magnitude of our average velocity. Now the vector, simply average velocity magnitude will be a root of Vx square plus Vy square, that is 1 square plus 2 square, which is equal to root 5. 4 plus 1 is 5. Let's say it is in meter per second, and tan alpha, as usual, I told you, opposite side by adjacent side when the two components are the rectangular components, because the two vectors have an angle 90 degree between them. So this will be 2 by 1, that is 2 by 1, which is 2. So you will notice here that tan alpha for delta r we got as 2, and for average velocity also tan alpha is 2, showing you that always this average velocity will have the same direction as delta r, that is the displacement vector, that is in the direction of motion. And the magnitude you will see is root 5 for velocity, and there we had root 20, delta r was root 20. So you can find the magnitude and the direction of both the displacement vectors and the velocity vector in this manner. Now the last topic that we will be dealing with for today is average acceleration and instantaneous acceleration, which again is not new to you because we did this in motion in one dimension. Only thing is here we deal with two-dimensional motion, because of which as acceleration is a vector quantity, in two dimension it will have components along the x-axis and components along the y-axis. So average acceleration A bar. Average acceleration A bar vector is delta v by delta t, change in velocity by change in time, which is v we know has components vx I cap and v by j cap. We just saw that. So that you may write delta vx by delta t along I cap plus delta vy by delta t along j cap. This is change in velocity, rate of change of velocity along the x-axis, which you may write as ax I cap plus rate of change of velocity along the y-axis, which is acceleration component along the y-axis, will give you the average acceleration. And again, instantaneous acceleration, as we have already defined, is the limiting value of average acceleration as the time interval tends to 0. Defined as instantaneous acceleration simply without the bar is equal to limit as time interval approaches 0, delta v by delta t, which is average acceleration, given by dv by dt, written as dv by dt. which is again d by dt of v is what? Vx I cap plus v by j cap. So you go back to what is dvx by dt will be rate of change of velocity along the x-axis written as ax I cap plus d by dt of vy, that is dvy by dt will be a by j cap, because that's acceleration along the instantaneous acceleration along the y-axis, that is acceleration here. Okay, so we know now that the instantaneous acceleration also has a component ax along the x-axis and component ay along the y-axis. One thing to be noted here is, if you look at the direction of acceleration, it always has to be in the direction of change in velocity, because how do we define acceleration? Acceleration is defined as delta v by delta t, right? So acceleration will have a direction in the direction of change in velocity, not in the direction of motion. For example, suppose let's say our body is moving in the xy plane in this manner. Okay. Now I told you, if you want to find out the velocity at an instant here, velocity is given in along the tangent. Velocity is given along the tangent here. So let me call this as the initial velocity, tangent. After some time the body has reached here, and if I now draw a tangent here, I get the final velocity of the body at some interval of time. Let's say this is at t1, this is at t2. Now change in velocity. So as you know, you can displace your vectors wherever you want. You can bring this vector to wherever you want, provided you do not change the magnitude of the vector, which is given by the length of that vector, and you should not change the direction. So if I now take this vector and displace it here, such that I am going to draw that vector here, so that the same magnitude and these two are parallel lines. Okay, maybe a little more here. They are same magnitude and parallel lines. Then I may represent this as the final velocity vector. So the change in velocity is given by this vector here, delta v, from initial velocity to final velocity. So we have, this is the direction of delta v, which means that will be the direction of acceleration. So delta v will be giving you the direction of acceleration of the body. So please note that acceleration, so this is the direction of motion of the body. At this instant, the displacement, the velocity is along the tangent. It is in the direction of motion of the body, but acceleration you see is in this direction. So acceleration is not in the direction of motion of the body, but is in the direction of change in velocity of the body. I will just give you one more example from our textbook, so that this concept becomes a little more clear to you. We have a sum in our textbook which tells you that the position of a particle is given by, vector r is given by 3t I cap plus 2t square j cap plus 5k cap. Okay. Now you will see that there are three axes here. So that means the position of the body is in space. So far we have been discussing about a body in a plane. Now if you have, this is the I, j and k axis. So if your body's position is represented with all the three axes, then that means it has an x, y and an z coordinate. That means your particle is in space. Okay, so now they are asking you to find out the instantaneous velocity and instantaneous acceleration at a time equal to 2 seconds. Okay, so you will see that the position vector is dependent on time, 3t, and here you have 2t square. So the x and y coordinates of that particle keeps changing with time. here 3t I cap and this is 2t square j cap. That means the position of the particle keeps changing with time along the x and y plane. The z component is independent of time. It's always constant in time. So we want to find the velocity and acceleration at t equal to 2 seconds. That means at a particular instant. So we are asked to find the instantaneous velocity, which means instantaneous velocity is given as dr by dt, which is d by dt of r is 3t I cap plus 2t square j cap plus 5k cap. Okay, so this is what we need to do. Now, I taught you the basic formulas that we need to differentiate. That is, two formulas I told you is d by dx of x raised to n is n into x raised to n minus 1. Also, d by dx of any constant is always equal to 0. So, if you know these two formulas, then we can easily differentiate a given expression. Okay. Now here our variable was x. So we apply the formula to x. X raised to n is n into x raised to n minus 1. Here we are differentiating with respect to time. So these formulas will be applied to t. I'll repeat. Here we are differentiating with respect to x. So our formulas are applied to x. X raised to n is n into x raised to n minus 1. Here we are differentiating with respect to time. So the same formulas are applied to t. So let's start that. This is equal to, now whenever you have a constant alone, then the differential of a constant is 0. But if your constant is appearing along with this t, then you just take 3 as a constant multiplied by, this is t raised to 1. So I'm going to apply the formula what I gave you here to t here. So t raised to n will be n into t raised to n minus 1, which is 1 into t raised to 1 minus 1 along the I cap, plus here again 2 is appearing along with t. So 2 into n is 2 into t raised to n minus 1 is 2 minus 1, plus you will see that 5 is just a number there, not appearing along with t. So differential of a constant will be 0. So since this is just a number here, it is 0. And this is along the j cap. So we now have t raised to 0 is 1. Anything raised to 0 is 1. So this is 3 I cap plus this is 2 into 2, that is 4. 2 minus 1 on top there will give you 1. So it is just t along j cap, and that is what represents your instantaneous velocity. Now to find out acceleration, this gives you the velocity vector in terms of I and j, the component. The velocity vector has a component 3 along the x-axis, 4t along the y-axis. Now acceleration is dv by dt, which is d by dt of 3 I cap plus 4t j cap. So again we go back to our formulas. Differentiation, 3 is appearing as a constant, just a number without t, so that is 0. Then here it is 4 into t raised to 1. T raised to 1 would be what? 1 into t raised to 1 minus 1, which is 1 into t raised to 0. Anything raised to 0 is 1. So we just have 4 into 1 j cap. So your acceleration is 4 j cap. Now if you represent this diagrammatically in a graph, it's going to look like this. We have velocity vector. This is the y-axis. This is the x-axis. Your velocity vector is represented here, vector v, having a component along the x-axis, that is 3 I cap, and a component along the y-axis, which is 4t j cap, which means this is going on changing with time, but this is a constant in time. So how will you, so now, and acceleration you will see is just 4j. That means your acceleration vector, the acceleration is only along this 4j cap. So your velocity vector is in the xy plane, whereas your acceleration is a constant in time, constant acceleration, because it does not depend on time. Here this component depends on time, but for our acceleration it is independent of time. It is a constant acceleration along the y-axis, whereas the velocity vector has both the x and y components. Now our question here was to find out the velocity, instantaneous velocity at t equal to 2 seconds. So at t equal to 2 seconds, you have, I'm going to substitute that vector will be, this is independent, so that is 3 cap plus t, if I substitute as 2, this will be 8 cap. And instantaneous acceleration, we realized, does not depend on t, it is a constant. So at every instant the acceleration is a constant acceleration along the positive y-axis. So we have this as 4 cap. Now let us find out the magnitude of this velocity at that instant and the direction of velocity at that instant. Okay. So at t equal to 2 seconds, we have, this is the y-axis, this is the x-axis. We have our velocity vector. This is 3 cap. And at 2 seconds, 4t would mean it is 8 cap. Let's take this as alpha. So that the magnitude of vector v here is root of vx square plus vy square. That will be root of 3 square is 9 plus this is 64. That will be root of 73. That will be, let's say, in meter per second, the magnitude. And to get the direction, tan alpha is equal to opposite side by the adjacent side, because we have the two rectangular components. So we have here as 8/3. And you can take a logbook and find out alpha there. So this is what we have here. I cap plus 4t cap. Okay. So you have found out your angle. So this is the velocity magnitude is root 73, and the direction that the velocity makes with the x-axis at 2 seconds is 8/3 tan alpha. So it is completely defined in terms of its direction and in terms of its velocity. So that's the end of our topic today. We'll continue in the next session very soon.